All right, let's get started. Okay, so we want to do the same thing we want to effectively do the same thing that we did on Wednesday. I got a spec sheet here, and we want to code it up with the state pattern. There is going to be a spot here where I don't know how to avoid a conditional. So this one wouldn't make a very good homework assignment because I can't ban conditionals. But we're going to use it as a lecture example where I can kind of cheat and use one conditional here. But what we want to build is a player class, and we're going to build some jump functionality. If you ever played and I'm thinking of a 2D platformer, if you ever played a 2D platformer, the jump mechanic is critically important to the game. You play a Mario game, the way Mario jumps is very complex. There's a lot of code that goes into that to make that jump just feel good when you're playing the game, to have it be responsive and just everything about it. We're not going to have too complex of a jump. We're going to have a pretty simple, pretty straightforward jump here because I have to fit this in a 50-minute lecture. But we're going to add some functionality to our thing. So let's just go through this. Talk about what this is first. So we're going to track the Y direction of the player. We're not going to do the X direction at all. Again, keeping it simple. But in the Y direction, the initial height of the player should be 0. We're going to have some left and right keys that when they're pressed, the player is going to start walking in that direction. And when it's released, the player is going to stop walking. When the jump button is pressed, so we have the concept of a jump button as well here, the vertical velocity is going to be set to 5. And then we're going to add some physics. We're going to keep the physics as simple as possible so we don't get bogged down with all the math. But while we're in the air, we should have some gravity that's applied at 10 units per second squared. I'm going to keep it vague and call it units so I don't have to do 9.81 and then use that in all my math and have all kinds of decimal and uneven numbers and everything. I want to stick with some whole numbers here just so my mind can handle it and I don't have to open up a spreadsheet while I'm in lecture. I don't want to. Sometimes I like doing that. Today, not so much. And we're going to apply this linearly. We're going to apply all physics linearly when we're coding. And the height is going to be updated before the gravity. So if we initially jump, our vertical velocity will be set to 5. And then if we update by a full second, we're going to say, okay, we're moving at velocity 5. We're starting at 0. So we're going to be, after 1 second, 5 units up in the air, where this is, I guess I should say units per second. So we're going to be 5 units in the air, and then we'll apply gravity. We'll decrease the velocity by 10 units since it's a full second, and say our velocity will be -5. So we're going to keep it simple. We're not going to apply any calculus. We're just going to say whatever time interval you told us we're updating the distance, the height, and then we're updating the velocity by applying gravity. Keeps the math nice and simple. It'll be 2 lines of math. This is a little bit of a cop-out, but really not that much. So if we're updating linearly, meaning that if a full second update, we have our delta t of 1 second, we're going to update our height and then update our velocity instead of using calculus. Well, with calculus, if we're taking the integral and doing integrals and derivatives and computing this as a continuous, nice, smooth curve, we're going to get some different results, of course. And when it's 1 full second, 1 full unit, it's going to be extremely different. It's going to be very different. But in calculus, what you do to fix this is not really magic at all. What you're doing is taking that dt and shrinking it down. You're shrinking it down until it's infinitely small and effectively computing things linearly the way we are, but with a delta t of effectively 0, as small as we can possibly get, and then updating over that interval at an infinitely small dt. And then you get all your calculus. But when we're actually running a game, when this game is actually being played, we're going to be playing it at 30 FPS, 60 FPS. If we have a 60 FPS game, 60 frames per second or 60 updates per second, our DT is only 1/60th of a second, which is not calculus, it's not perfect, but it's pretty close. So when the player is playing a game at 60 FPS and physics updates are happening linearly without applying any calculus, the player's not even going to notice. It's going to be so close to your nice smooth. The player's going to see nice smooth parabolas and everything. It's going to be so close to the actual what you would get with calculus that's not really going to matter. Now, depending on your actual game, if your game really depends on accurate physics, you want to do something different. But you actually get away with linear updates like this. In our testing, our delta t is going to be way too big to be practical, and the numbers are going to be way off just for testing. But actually running this game actually wouldn't matter. Not too much anyway. And then we should jump higher if we're walking instead of standing. So if we're walking either left or right, and since the x direction doesn't matter, we're not doing, or I shouldn't say doesn't matter, but since we're not doing anything with the x direction to keep this simplified, we don't care if we're moving left or right, but if we're walking at all, that initial velocity should be 10 instead of 5. So we want to jump higher if we're walking, pretty standard for a 2D platformer. And we should stop falling when the height is 0. Once we land back on the ground, we should stop falling. That velocity should be zeroed out. So that's what we want to build at first. And we want to build up to this double jump functionality after we build all this. A lot of times when I do this lecture, I pull this like 2/3 of the way through the lecture. I'm like, what if we had to add a double jump? And then it's this big surprise. Not going to do any surprises here. This is what we're leading up to, is a double jump. This is when you jump in the air, you can jump one additional time, but no more than that. And then you have to land again to reset your double jump. So and your double jump velocity should be 5, the same as a standing jump. So we should think of how are we going to build that double jump as well. Which AO task is the hardest, in my opinion? Probably calculator. I got to button up the design of AO Test 3 over the weekend so it can be released by Monday. But I don't think that one's going to be hard. I think it's going to be more of a break, which I think we could all use. Not strictly easy, but probably not as hard as I don't know, was AO Test 1 hard? That one, I'm kind of on the fence about of how that one was perceived, if that one was hard. Because it could have been, if you're good at debugging, the AO Task 1 should have been pretty easy. And AO Task 3 should be closer to that than Calculator. Calculator is pretty tough, in my opinion. So this is what we want to build, and we're going to test it first. I actually have tests here. Before we get through that, I did add some TV tests also to the example on Wednesday. I felt bad that I didn't have testing. I talk about testing all semester, and then there's no way we had time to do this in lecture, so I added it after the fact. When we're testing a class that applies the state pattern, we're only calling the API methods. The same is true with your calculator. Of course, these lectures are designed to parallel calculator. You have the API methods given in the calculator class, and those are the only ones you call in your testing. You don't call any other methods at all. And I say this so many times, there's always a handful of students every semester that will create a method that's not in the handout and then call that method in their tests. That method doesn't exist in my solutions in Autolab, with high probability at least. It's not going to exist. So we're sticking with the API methods. Those are the ones we agree will exist, and they're the ones that correlate with the buttons and the display. So same thing with the TV. I'm going to call my 5 API methods. Current volume is my only way to access the state of the TV in any way. So this is my one thing that I can assert. Does current volume return what it's supposed to return? With your calculator, does display number return what it's supposed to return? That's the only thing you can assert in your homework. You're going to push buttons and make sure that the display number is correct. So the volume should be initially 0 because the TV's off. Volume up, down, mute, don't do anything. It's all 0. Turn the TV on. It should be at that initial 5, and so on. I'm going to push a whole bunch of buttons. Push a button, check the volume. Push a button, check the volume. Push a button, check the volume. And check all my functionality. for the television. The one difference with your calculator is with the TV, all of the functionality is defined. So after every single button press, I know what the current volume should be, and I can assert it. There's, I think, just one time where I'm pressing 2 buttons before I assert, but I could assert in the middle here too, if I wanted to, which I don't know why I didn't. I could have asserted after every single button press. With your calculator, that's not true. There is the undefined behavior, so make sure you're not asserting the display number when you're in any of those undefined behavior, I want to say states, but that means so much during the state pattern. When you're in one of those situations where it's undefined behavior. So the defined behavior for display button is only when you're entering the first number ever. So you create a new calculator, you can assert that display number is 0.0. You can press the 1 button, assert that display number is 1. Hit 0, assert that the display number is 10. Hit 0, assert that it's 100. Hit point, assert that it's 100. Hit 5, assert that it's 100.5. And then once you hit an operator button, so you hit plus, the display number is now undefined. We don't define what it's supposed to be, what's supposed to be displayed at that point, so you can't assert it. And then you're entering another number, so you enter 500. All of that is undefined. We don't know what is supposed to be displayed, so you're not asserting anything until you hit the equal button again. So when you hit the equal button, and now you can finally assert the display number again. And it should be, if I remember my numbers, 600.5. You can assert that the right thing was returned from the operation. And only after you enter that first number, you can only ever assert it after you hit the equal sign. And you should assert it after each equal press. If you're testing the multiple equals for application objective 2, and you hit equal 3 times, assert that the right thing is displayed after each one of those equals. Okay, back to Jumper. So with Jumper, we have a test suite here, which I wrote in the last lecture, but it's kind of boring watching me type it out, so I'll explain this one. But I'll type all the code for the state pattern. So I have a helper method here. Should I do my API first? Let me do the API first to get rid of all these errors so we know what these methods are supposed to be. Let's do our API. Let's go through this spec sheet and figure out what methods can be called on our player. So right away, start with a height of 0. We already have one of our getter methods. We can get what the height should be. So height and give it a default return 0.0. Walk when left or right are pressed and stop when they're released. So public. So I want to know when they're pressed and when they're released is going to give me 2 pieces of information. So we're going to get both of those as inputs to our class. So public left down. Public void left up. Public void right. What am I doing? Right down. Right down and right up. AO2 without strings would be pretty tough, but I'm confident that student can do it. Jump, so we have the idea of a jump button. Public void jump, and I'm going to try to remember what I named all these methods because they're being called in my testing. As long as I name all these right, all our errors should go away in the end. Jumping will set their vertical velocity to 5 units per second, so I need another method for that velocity. Public double vertical velocity, return 0.0. Vertical velocity. While in the air, gravity of 10 units per second squared will be applied linearly and the height will be updated. while we're in the air. So public void, we don't expect anything to be returned from all these void methods. Again, a button press doesn't return anything. And update, this is only going to change when we update while in the air. It's only going to change the state of the player. And update needs some sense of time, so we're going to say this will update some number of seconds, and I'll spell it out instead of using dt, delta time in seconds. I guess we could do seconds elapsed. So how much time has elapsed since the previous update? Jump higher if walking, stop when their height is 0, and double jump velocity. None of those sound like method calls to me. Sounds like more or less state behavior. And let's see if we got all of our errors gone. Cool. I named them the same thing I did before. Consistency. All right, so let's take a look at our test suite and see what our player is supposed to do, because we got more moving pieces than we did with the TV. So let's make sure we all agree on what is supposed to happen, which is one of the big benefits of writing your test before your code. If you're using test-driven development, you're forced to think about what your code is supposed to do before you get halfway through coding it. So you don't want to get halfway through coding something and then get to a spot where you're like, oh, I don't know what this thing's supposed to do. And then whatever decision you make, say, okay, I think it should do this. Have that decision affect all of the code you already wrote, and now you have to rewrite all that code. It's not fun. It's never fun to do that. If you write your test first, you're forced to think about those things before you're in too deep, that it's really painful to go back. So I have a helper method. We're going to continuously check the height and velocity of the player. So I want a helper method just to clean up my code a bit. I'm going to call check player that I expect this height and this velocity, instead of pasting these two lines of code over and over again. And this also allows me to put epsilon in a constant just one time. I mean, I guess I could do that anyway. We're going to have one epsilon, so if I ever want to change my epsilon, say I want tighter precision here, I want to make sure my physics engine is getting me more precise numbers than I was testing, I can add a few zeros here. If I'm comfortable with a lot of tolerance here, I can decrease it. I change that one time, and it cascades through my entire test suite. So we create a player. Player's initially standing on the ground, no velocity, no height. If we hit the jump button, but we don't update yet, our height should still be 0. We're still on the ground, but our velocity is going to be 5.0, according to the spec sheet. And then if we have 1 second elapse, 1 second elapses, we have a vertical velocity of 5. We're computing height before applying gravity. So with this velocity, that velocity will be applied over the entire 1 second, and we'll have a height of 5.0. And then our gravity of -10 will be applied, so that 5 velocity is going to change to a -5, our velocity minus gravity times elapsed time. Another second goes by, we should be back on the ground. I have a height of 5 and velocity of -5 after another second. We should be back on the ground, and that should zero out our expected velocity. A common bug here would be having having a velocity of -15. We want to make sure we don't have that bug. We want to make sure that's zeroed out when we land. Then if we push left and jump, same thing, but we're going to have initial velocity of 10. A second elapses. Our height's going to be 10, and our expected velocity is going to be 0. So this minus our gravity of 10 times a second is going to be 0. Another second, we're going to still be 10 in the air because our velocity is 0 over that 1 second, but our gravity kicks in and gives us -10 expected velocity. Another second, we're going to be back on the ground. So and this is a case where there are tons of edge cases, tons of extra testing we can do with this. There's a fairly complex functionality that would take a lot of testing. I'm getting a test suite down here so we can test the very, very basic functionality, but hopefully there's some edge cases that are screaming out at you that we could be testing. Lowering the update interval, getting some results that are decimal results. My code could be truncating every single value, but since all my expected values are whole numbers, I would never find out. I would never find that bug. But I just want to get some test suite down for this. And then I'm going to stop. Oh, actually, this doesn't need to be here, does it? So I am going to say when a player lands, I'll add that to the spec sheet even. When a player lands, they are standing. And there are a few things we're going to have to kind of assume about the buttons that they're pressing. We're going to assume they're not pressing left or right when they land. Do we have to assume that? Well, we're going to. Where are we? Right here. And then while we're on the ground, any length update shouldn't do anything. We're just on the ground. So if I update for 10 seconds and the player was just standing there, they should still be standing there. And then we jump. Do the same thing that we did from our standing jump, except we're going to jump again. We're going to use our double jump, which we expect that to set the velocity back to 5. And then we're going to update another second. We should jump higher in the air. After we use that double jump, we should be higher in the air. But our expected velocity after gravity is going to be -5 again. And then no matter how many times we hit the jump button, it doesn't do anything. We can only double jump once while we're in the air until we land again. So we can hit jump a whole bunch of times. Nothing's going to change. And then just some update to make sure that we're landing back on the ground. And then we should test if we jump again, does our double jump reset, making sure that we get our double jump back when we jump again. So a lot more we can test here, but just to get this to fit in a lecture, we're going to cap it at that. So let's set up our state pattern. I like to do this in a separate directory. And collapse these other ones. New Java class player state is going to be an interface. And we want to grab all these methods, throw them in the interface, and make them abstract, which is maybe the most tedious part of watching me do this. I just got to delete these and make these abstract. Oh, it would be a perfect time for a question. No, we don't got one. I'm removing my publics too. And format. All right, so we got our state, and now let's go through the spec sheet again and figure out what states we're going to need. Actually, I don't need to do that yet. And figure out what states we're going to need. All right, so each player should start with a height of 0. Walk left and right when keys are pressed, and stop walking when right and left are released. So sounds like a walking state to me. Where we're going to have some different behavior. If we're walking, we're going to jump with a higher velocity than if we're not. So I have what sounds like a walking state, which will implement the player state interface. And let's get our methods in here. Left and right, jump when jump is pressed. Jumping will set their initial velocity to 5. While in the air, so it sounds like we're going to have different functionality while we're in the air. Sounds like a state that I like to call jumping. Jump higher if walking instead of standing still. Sounds like a good name for my other state, standing. Stop when their height is 0. When the player lands, they're standing. And assume left and right are not pressed. We can keep adding to this, but just some simplifying assumptions. And double jump while in the air, double jump velocity. Okay. So standing, walking, and jumping sound like our states, where we're initially standing until the left or right buttons are pressed. And we're not going to, like, we could have a walking left, walking right state, but for our purposes, we're just going to say if they're walking, that's a different state, because we're only concerned about the jump height for our example here. This example can get very complex if we add like all the functionality. I used to do this as a different example. I'd have all the code written before lecture, and it would be an actual game, and we'd jump around and stuff. It was so much that I don't think anybody got anything out of it, because there were way too many states, way too much going on. So we're simplifying it so we can actually get something out of it. And just so I'm not pulling any punches, this will be, right, let's get this set up. This will be very similar to the TV situation, the TV thing last time, where it seems like we have 3 states. We will actually end up having 4. Kudos to you if you can see the 4th state already. But we're going to have a 4th state. So let's go through this with our 3 states and then figure out where we're going to get in a situation where we have a different set of functionality that we don't have in these 3 states. I like to, well, first we got to set this up. I like to start in my initial state, so we'll start in the standing state for our functionality, and let's just get this whole thing set up. We did this last time, so I won't have too much commentary on this, but let me just get the code down here. So we're going to have an instance of a player. We're going to import that. I'm going to make sure I import the right one, because we have a lot of player classes, as it turns out, this semester. Generate my constructor. And I'm going to grab this for all 3 of my classes, all 3 states. This is jumping. This is walking. I want these in the order that I'm going to code them in. Player doesn't need to be on this side. Player state is done. We're not going to have to look at that anymore. Test jumping can come over here. STV we're not going to look at. And we need our state variable here, private player state equals our initial state is going to be standing, and pass a reference of this. And I want my public void state transition, which is going to take a new player state, new state, this dot state equals new state. And then I forgot to do this in the last lecture, so let's remember it here. Actually defer to our state for functionality instead of having our default stubbed out methods. This dot state dot vertical velocity dot left down dot left up dot right down dot right up dot jump dot update seconds elapsed. Okay, so there's most of our player class. We'll have to revisit it in a bit. But let's go back to our spec sheet and start implementing our methods. Here's where things start getting easy. We got our setup, figuring out our API, figuring out what states to create. Those are, I think, the tougher parts of the state pattern. But now when it's time to actually implement our methods, things get a little bit easier. We can take a breather and say, okay, I know how to do this. If I'm in the standing state and somebody asks me for my height, what do I do? Well, I'm just going to do that default thing, return in 0. Sounds great to me. If I'm standing on the ground, my height should be 0. If I'm standing on the ground, my vertical velocity is 0. So those two are easy. If somebody presses the left button, and we're going to make some assumptions here, you'll see. If somebody presses the left button, this dot player dot state transition. We're going to transition into the walking state. New walking, this dot player. And when left is released, when we're in the standing state and the left button is released, nothing should happen. If we're standing still, presumably the left and right keys are already up. They're not being pressed at the time, or else we wouldn't be in the standing state. So nothing's going to happen here. Right down is going to do the same thing. We're not keeping track of left versus right. So we're going to transition to the walking state. Right is assumed to be already up if we're in the standing state. When we jump, we're going to transition to the jumping state. And when we update, if we're on the ground and we need to update our vertical velocity and our height, nothing should happen. What are we supposed to do? Nothing. We're not in the air. And specifically, well in the air, that's when things are going to be applied. We don't change anything with physics when we're standing on the ground. We could, if we were going to make this more complex, this is the standing state anyway, but in the walking state, we could say update is going to update your x direction, but we're not even going to go there. So that's our standing state. Fairly straightforward. Most of our methods do nothing, and 3 state transitions. Let's meander over to the walk-in state. Oh, I meant to make these final. Nobody's going to care, right? Those could be final. They're final in the repo for what it's worth. All right, so walking state, our height, 0.0. We're walking on the ground. Our vertical velocity, 0.0. Hopefully we don't have any negative velocity clipping into the ground. That's a bug that everybody's going to report to us. And if we're walking, hopefully we're not going up in the air. Now, no, we don't even have to go down that tangent. I'll go down a little bit, but we could be walking up or down a slope, and our vertical velocity could be changing. But we're going to assume a flat surface, a flat ground. So left down, here's where we're going to make that assumption. Left down and right down, we're going to assume that one of these buttons is already down. And we're also going to assume a D-pad. These are just simplifying assumptions, but I do have some logic of why it makes sense. We're going to assume a D-pad where you can't hold both left and right down at the same time. Bless you. If you could, it would mess with our code a little bit. We'd have to add another state or two to be able to handle that. So we're going to say they can't be both held down at the same time. So if left is down and right was being held down, that means right's coming up and left's going down, which means you're going to still be in the walking state. Nothing's going to change. Nothing happens. Same with right down. And then left up, we're going to transition to the standing state. And same with right up. If the player's holding left, right up shouldn't ever be called because it's already up. So if right up is being called, that means right was being held down, and it's coming up. That means we're going into the standing state. So those methods are done. Jump is going to be a transition to the jumping state. And update still doesn't do anything. That's where we could update our x direction, but we're not going to bother for what we're doing here. I'm done with this one, kind of. We'll have to revisit those. And then the jumping state. This is the most complicated state in this. Not that it gets overly complicated, but this is the toughest one that we have to implement. And right off the bat, we have height and vertical velocity. We're going to want to return some variable. So we can have some variable which is going to be part of the state of an object that's going to be updated when update is called. So we have to set up how to do this. We have some choices here. Since it's inherently the player's height and the player's vertical velocity, to me it makes most sense to put these variables in the player class. So let's head back to the player class and get some height and velocity. Private double height. Initially 0.0, private double velocity, because I don't want to type vertical every time, we're going to assume that it's vertical velocity. And then get me some getters and setters for these things. Getters and setters look good. And when we want to return the height, we're going to ask the player for its height. This dot player dot get height. This dot player dot get velocity. Get back down to our spec sheet. Because we have a couple lines here, we have our physics that we're going to have to implement here. Left down, left up, right down, right up. We're going to assume that these do nothing in the air. If you're jumping, we're going to assume that the player lifts off the buttons, which is a strong assumption. That's one that I can't really justify other than I don't have time to add another state. Because when they land, we would either have to transition to the walking state or the standing state, depending on whether or not they have a button held down or not. We're just going to say they always land in the standing state, just to keep that a little bit simpler. So none of these buttons are going to do anything. Otherwise, we'd have an in the air while moving left or right, and then in an air while not moving left and right. And have those as two different states, and then have these buttons transition between those two states. We could do all that with an extra state. I just don't want to add that state because this lecture is already timed good for 50 minutes. Jump, this is where we're not going to do it yet. We're not really set up to do it, but this is where we're going to do our double jump. And then update. Let's get update down there. So update and jump are the two things that we have left to do. Well, we have a few things left. So update is going to apply 10 units of gravity, and it's going to update the height before gravity. And this is where I don't like it, but I don't have a good way to avoid it. I will use an if statement in this method. So what are we doing? This dot player dot, I'm going to update the height first. So this dot player dot set height. This dot player dot get height plus this dot player dot get velocity times elapsed seconds elapsed. So that's going to give me a linear progression. Whatever my velocity is, multiply that by how many seconds, and that's going to be my additional height that I gain. Or if velocity is negative, how much height I drop. And I'm taking advantage, I didn't mention this the last one, hopefully everybody caught it, but I'm taking advantage of order of operations. Multiplication is going to happen before addition. Programming is just like math. Your PEMDAS applies. So this dot player dot set, then we want to apply gravity. Set velocity equals this dot player dot get velocity minus, and I want a constant for this, double gravitational constant is going to be 10.0. I don't want a magic number. So gravitational constant times seconds elapsed. Again, with order of operations. And then, I don't like it, but I don't have a great way of avoiding it. If this dot player dot get height is less than, and we'll allow some tolerance here, but if we're on the ground, this dot player dot set height to 0.0. Just in case we clipped into the ground, we want to make sure that that's fixed before the player sees that. So we're going to set it to 0.0. This dot player dot set velocity to 0.0. This dot player dot, and here's where we're going to use that assumption that the player lets go of the buttons in the air, which is, again, a strong assumption, to a new standing state. Something that we easily could handle, it would just take too much time. So there's our physics. We're going to update our height, update our velocity according to gravity, and then check if we're on the ground, then do these updates. And this one, I don't think there is a way to get rid of this. Maybe there is some really fancy way to get rid of it that I'm not seeing. But there are certain features that will require conditionals in one way or another. I think we might be able to get rid of this one the way we did last time, where we call methods that use conditionals and do it that way, have some fancy way of doing it like that. But inherently, there are programs that will have to have conditionals, certain problems that will have to have conditionals, like mathematically, provably need conditionals. So the state pattern can't be applied to everything with purely no conditionals. The homework assignments are carefully curated to make sure that you're not gonna want a conditional after applying the state pattern. Okay, so we got that. There's one big thing that we're missing, though, is... Oh, my goodness. Stop. Oh, no, I'm going blind. There it is. Is the difference between the walking velocity and the standing velocity. Right now, we have no concept of this velocity at all. Velocity is just always 0 in our code. If we ran this code, velocity is always 100% of the time 0. So we need some way to handle that. We have a lot of options for this, a lot of different things we could do. The way I'll do it, just because I want to show, just because this is the point that I want to make, is I'm going to add it to the constructor of the jumping class. I'm going to say double, I'll call it initial velocity. And then I'm going to set the player's velocity to that initial velocity. This dot player dot set velocity to that initial velocity. The point I want to make is, in your states, you have full control over how you build these things. If you don't want to build your states the way that I'm doing it, you don't want to set up the state pattern this way, don't. Set it up a different way. Paul does things a little bit different than I do. If you want to do it the way he does it, if you don't want to do it the way either of us do it, you have full control, because your states are never accessed directly from my testing, and your states are never accessed directly from your testing either. You have full control on how you implement the state pattern, and they are full classes. So everything available to you, different instance variables, constructor parameters, extra methods, whatever you want to do, it's on the table. It's available to you. So I'm going to take advantage of that and slap another constructor parameter here. I should have errors over here. In my standing class, that initial velocity is 5.0. In my walking class, it's going to be 10.0. And now we have that feature built. Let's run our test suite. It should be broken. Shouldn't have been that broken. I had that in a standing state transition. I'm a dummy. 10.0. But our test suite should fail. But it should fail right where we expect it to fail, which is, this is where it's failing, and that's exactly where we expect it to fail. So we're getting past all of this testing. We did pretty good on most of this, but when we're jumping, we're in the air, and then we're doing our double jump. We haven't implemented that feature yet, so I'd be a little concerned if this did pass, because we have a whole feature that's missing. So let's tackle our double jump. This is good confirmation, or at least I get a little bit of confidence. This isn't a very strong test suite, so not a lot of confidence, but a little confidence that all that's coded correctly. But we don't have a double jump. Let's get a double jump in here. When we're jumping, we want to double jump. So there's a temptation to say, what's on my clipboard? Ooh, state transition. So there's a temptation to do this. Jumping this dot player, and our double jump velocity is 5.0. But we need a way to disable the double jump after you double jump one time. And this isn't going to do it. This is going to let us jump an infinite number of times while we're in the air. which is going to be a ridiculous bug. As soon as the first player plays our game, they're going to find that and just cheese the entire game. That's a huge bug to have. We don't want that. So we want a new state. I shouldn't just jump to that. So we have a different set of behavior that isn't captured in any of our states. It's mostly the jumping behavior, but this jump method should do something else. So I'm going to create a new state because I have a different set of functionality, and I'm restricting myself from not using conditionals. This one's, by the way, just begging for a conditional. Just have a Boolean right here, a Boolean that says, did you use your double jump or not? And then have one conditional here. If you can use one conditional to avoid an entire state, and that one conditional is only controlling one line of code, you're going to use the conditional before you create another state. But if we have this artificial restriction of no conditionals, I'm going to add a new state. I'm going to lovingly call it jumping after double jump. And I'm going to, noting that this is almost identical to the jumping state, and the fact that I understand inheritance like you all do, extends jumping is what I want to do. I'm just going to extend jumping. I'm going to get an error because I need to implement the constructor, which I'm going to take the default behavior here, which just takes in the parameters and forwards it to the superclass constructor. I don't need to do anything different in this class except I'm going to override public void jump. And what I want the jump button to do after the double jump is used is nothing. This is the whole method. So all I want this state to do is to disable the jump button after it's been used, which is very similar to your decimal button. You hit the decimal once on the calculator, you want that to mean something. That's where you're putting the decimal point, and then you enter some more numbers, start entering the decimal portion of the number, and then you hit the decimal button 100 more times. That button should be disabled. It shouldn't do anything, or else you're going to have some crazy bugs in your code. So if you extend whatever state you were in, disable that button. Otherwise, everything else is the same. You're going to get that functionality of turning off the button without a conditional. Let's run our tests, and we should get a beautiful green check mark here. Oh, my goodness. So I know what I did. I never updated my jumping state. Oh, my timing, though. We were right at the end. When we jump, we need to be in